Frizzell, W2MAF, in the University of Scranton, and also the founder of HamSci. So, Nathaniel, welcome back to the Mercer County Amateur Radio Club, and thank you for being here. Over to you.
Thank you so much. I really appreciate it. Thank you for everyone coming tonight. Can you hear me okay?
Yes.
Great. Let me start my presentation. And let me get the screen sharing going here. Do you see the presentation full screen?
Yeah.
No.
No.
We have,
Yeah.
The next slide in the notes up.
Yeah, the next slide and notes up. Okay. Let's try this again.
Now you're full screen.
No, not quite.
All right, try this. And then we'll try that. How is that?
Yeah.
All right. Thank you very much, everyone. I really appreciate it. So yes, my name is Nathaniel Frizzell. I'm Whiskey 2 November Alpha Foxtrot, and I am the founder and leader of the HamSci community, the Ham Radio Science Citizen Investigation. I'm also a professor of physics and engineering at the University of Scranton in Scranton, Pennsylvania. And I'm very grateful to Tim Duffy, K3LR, for both his invitation tonight and his continued support and DX engineering support of HamSci's activities. So what is HamSci? HamSci is the Ham Radio Science Citizen Investigation. We're a group or a collective that allows university researchers to collaborate with the amateur radio community in scientific investigations. And so we want to advance scientific research and understanding through amateur radio activities, encourage development of new technologies to support this research, and provide educational opportunities for amateur radio community and the general public. And just a quick background of how I got here and how this all started. I really got into this because I became interested in ham radio as a Boy Scout back in 7th or 8th grade at a jamboree on the air. And that just really inspired me to eventually get my ham radio license. I eventually taught ham radio and radio merit badge at Forestburg Scout Reservation for many years, and I just kept doing it until I got my PhD in ionospheric physics at Virginia Tech in electrical engineering. And when I was in grad school, I figured out ways to connect ham radio with science and create HamSci. So that's where all this came from. So I'm going to go over how we're going to what we're going to be doing for the upcoming eclipse. I'm going to provide some background about the ionosphere. For those of you who have been hams for a long time, this is probably old hat, but for people who might be new in the audience, this might be interesting. So the ionosphere is the electrified layer of the upper atmosphere that we can use to let our signals, our high frequency radio signals, travel around the globe. It's created by starting with the neutral Earth's atmosphere, and during the day, the sun hits that, and the ultraviolet and X-ray energy from the sun will ionize the upper atmosphere. It'll knock electrons off of the off of the neutral particles, and you'll get free-floating electrons and free-floating positive ions. And during the day, the ionosphere will stratify into 4 different layers: the D layer, which is closest to Earth, the E layer, then the F1 and the F2 layer. At night, the sun goes away, but the ionosphere does not totally go away. Ion production stops. The electrons, some of the electrons will find their way back to some of the neutral ion, some of the positive ions. They'll recombine, turn into neutrals. The ionosphere will become less dense and weaker. You will get mostly just an E region and an F region. So this is important for eclipses, because what's going to happen during an eclipse is the moon is going to go in front of the sun in such a way that the shadow of the moon will go on the Earth and create a period of temporary night-like conditions. And so you're going to have somewhat night-like ionosphere in just that localized region, and that's going to affect our radio signals. So this is a diagram, let me pause this for a minute, that we call a ray trace diagram. this is predicting how our radio signals will travel through the ionosphere. This is a ray trace for 14.03 megahertz. Here at the origin, I have the station located in Florida, AA2MF, and I have over here at the other end of the red line, WE9V in Wisconsin. And then the colors you see in the background are plasma frequency, which is related to electron density. And this is coming from a model called SAMI3. This is a physics-based model of the ionosphere. We have on the y-axis altitude from 0 to 500 kilometers, and the x-axis you have ground range in kilometers from 0 to 2,500 kilometers, and the station is about 1,700 kilometers away. So you can see on 14 megahertz, the ray trace predicts that the radio ray, the 14 megahertz ray, will go up, it'll refract off of the E region in this case, go back down and reach Wisconsin. And when you see a red line appear here, the computer program is predicting that the stations will be able to talk with each other. I'm going to play this movie now, and what we're simulating here is actually the eclipse back in 2017. So right now you see a period right before the eclipse. When the eclipse comes on, you're going to see that the colors become more muted because the ionospheric electron densities are being reduced. That will happen for a time, and then when the eclipse is over, the electron densities will build up, the colors will become bright again, the eclipse will be over. When the eclipse is occurring, you're going to see less refraction of these radio waves, and they're going to escape out into space. And then AA2MF will no longer be able to talk to WE9V. So let's see that go. Here comes the eclipse. All the rays escape into space, communications breaks down, and then it comes back. This is a model of what happens on 14 megahertz between Wisconsin and Florida during the 2017 eclipse. I'll play that one more time. So one thing that this is demonstrating how refraction of a radio signal changes as a function of electron density. So you can see if you have lower electron densities, the radio waves will escape out into space or refract less. If what we're doing here is we're changing electron densities, but we're holding the frequency constant. The refraction is also a function of frequency. So in this ray trace, we're holding the electron density constant, but I'm showing how the refraction changes as a function of frequency. Between 1.5 to about 30 megahertz or so, generally, the higher you go in frequency, the less refraction you get. Look at this ray trace diagram for 15 megahertz. You can see that it takes about one hop with this particular ionosphere to go 1,500 kilometers. If you keep the same background ionosphere, but just lower your operating frequency to 10 megahertz, you can see that you get more refraction. It takes 2 hops to go the same distance. So these are the reasons that the propagation is different for different bands. It's also the reason that the propagation is different for different times of day versus night. Now in HamSci, one of the things we try to do is not just look at the radio propagation, but we try to use radio propagation as a tool for remote sensing what's going on in the ionosphere. So we can use these same models and these cartoons to help us look at the ham radio data that we collect and tell you something about what's going on in the ionosphere between the radio state,
Would you lost audio report? No, I think he froze because everybody else is still moving. Okay.
started in the Northwest United States and went southeast and over to here, and just in a period of about a few hours. That was August 21st, 2017. And from a science perspective, eclipses are a rare controlled experiment, because aside from dawn, dusk, and the seasons, there are very few cases where we know ahead of time how much solar energy is going to be input into the upper atmosphere. Solar flares, geomagnetic storms, and others are random events that we cannot predict, but we can calculate eclipses with great accuracy ahead of time, and so these can be considered a controlled ionospheric experiment. So that's why this is extremely interesting to scientists. So for the 2017 eclipse, we had some research questions. We want to know, can we use HF ham radio communications to observe the eclipse effects on the ionosphere? Can we use the data model comparisons to better understand the ham radio data and to constrain or calibrate the model? And I personally was very interested to know, can we do all of this and also create a fun ham radio event, create a contest or a QSO party? So that's where the first solar eclipse QSO party came from. This was on August 21st from 1400 to 2200 UT, and we made it contest-like. So you got 2 points CW for CW or digital QSOs, 1 point for phone, and then I wanted to encourage as many paths as possible across the eclipse. So we said multiply your score by the number of grid squares. And to observe and collect the data, we use data from the Reverse Speaking Network, PSK Reporter, WhisperNet, and also participant-supported submitted logs. And we had really good success from the 2017 event. We had 570 successfully parsed logs, almost 30,000 QSOs in those logs, and almost 5,000 unique call signs and ADDX entities. So I was really happy with that. From the Reverse Speaking Network, WhisperNet, and PSK Reporter. So these are all automated networks of automated stations that are constantly monitoring amateur radio traffic. Reverse Speaking Network monitors primarily CW traffic, but also RIDI and some other digital modes. WhisperNet monitors just the weak signal propagation reporting network mode. PSK Reporter monitors pretty much all of the other digital modes. At the end of the QSO party in 2017, we had over 600,000 spots or observed communications from the RBN, from WhisperNet, and over 1.2 million from PSK Reporter. So this provided a really nice base of observations for looking at. So these are just the RBN spots from the 2017 solar eclipse QSO party. The black dots are all of the CW transmitters active during the SEQP. The blue stars are the locations of the Reverse Speaking Network automated receivers in operation at the time, and every colored dot represents the midpoint between a transmitter and a receiver for a communication or a spot observed. And the reason I'm plotting the midpoint there is because we're assuming that's where the signal refracts off of the ionosphere, so that's where we're making our ionospheric measurement. In this particular map, I'm color coding all of the dots, all of the spots, by how much eclipse, the maximum amount of eclipse that was observed in that particular location, where this dark red is 100% eclipsed. So here's some actual data from the 2017 eclipse on top, this top panel here. This is showing the 14 megahertz band only. On the x-axis, we have time relative to maximum eclipse. So the eclipse curve is this white dotted curve right here. When the curve is lowest, that's maximum eclipse, meaning the least amount of light. This is an hour and a half before the eclipse maximum over here. This is an hour and a half after eclipse maximum. And then the y-axis represents distance between transmitter and receiver. So you can see an hour and a half before the eclipse, 20 meters, 14 megahertz was very active with distances between 1,000 to 2,000 kilometers. And that continued up until about 45 minutes before eclipse maximum, where you can see we're starting to lose communications there as the ionosphere weakens and the band shuts down. As you go on in time, as the eclipse is over, you get the ionosphere to build back up, and you get the QSO counts to increase again towards the end of the day. So you see recovery of the ionosphere. Down on the bottom here, this is actually a model. So this is the same ray tracing model that I showed you the movie of before, but what we did was we calculated the ray traces between we created a theoretical grid of transmitters across the whole United States, and then we tested every link between those transmitters and a receive RBN station using the ray tracing. And if a connection was observed, we included that in our count. And so you can see that the model matches the observations really quite well. The observations are a little bit noisier and a little bit more spread, but generally we did a good job getting this. So in order to get this, let's look at what happened over multiple bands, not just 20 meters. So on the left here, these are the actual observations. It's in the same format as before. So all of these plots go from an hour and a half before the eclipse to an hour and a half after the eclipse. And the y-axis goes from 0 to 3,000 kilometers in distance. And so here's the 20 meters that we just talked about. 7 megahertz, you see a little different behavior. Instead of the band shutting down during the eclipse, the band went long. So there's less refraction. The rays were able to communicate to farther distances, but they did not escape into space. When the eclipse was over, the band recovered. You see the normal distances of about typically 500 kilometers between transmitter and receiver. For the lower bands, 3.5 megahertz and 1.8 megahertz, you see very few communications before and after the eclipse, presumably because the D region is causing absorption there. But during the eclipse, you actually see the bands open up just like you would at night. So this really captures everything very nicely. Now with the modeling, to get the good result I showed you before, I actually had to split the model results up into E region refractions and F region refractions. So what this is showing here, this is showing the model results just for E region refractions. So only rays that are refracting off the ionosphere at less than 125 kilometers altitude. We get good agreement between 20 meters, but the rest of the bands show poor agreement there. So this is suggesting that most of the 14 megahertz communications were off of the E region. If we look at the F region of the model, we get good agreement on 7 and 3.5 megahertz, suggesting that those are refracting off of the F region, while 20 meters does not have good agreement. 160 meters didn't agree with either of the results. I think that's because we actually had the electron densities set too high in the model, and likely if we if we reduce the electron densities a little bit, which might be a little bit more realistic, we'd probably get good agreement on 1.8 megahertz as well. So I think the conclusions for the 2014 eclipse, the 20 meter band refracted off of the E region ionosphere with very low elevation angles. And I think this was perhaps a little surprising, but that's what the result showed. And the 1.8 through 7 megahertz bands refracted off of the F region with high elevation angles. And you saw how the bands were affected in terms of timing for the eclipse. You pretty much saw effects of 45 minutes to a half hour before, up to a half hour to 45 minutes after the eclipse. So we have the chance to do this again. There's going to be 2 solar eclipses coming up very soon. The first one is just a few weeks away. That's going to be October 14th. We have an annular eclipse that's going to again go from northwest to southeast, this time exiting through Texas. And then we have a total solar eclipse this April 8th going from southwest up to northeast, exiting through Maine and Canada up here. So 2 really nice opportunities to make measurements again, and also have a nice QSO party. So what are the different types of eclipses we're seeing here? So a total solar eclipse is when the disk of the moon completely covers the chromosphere, the main disk of the sun, and you can just see the corona. So that's what's going to happen in April. In October, we're going to have an annular eclipse where the disk of the moon is inside of the sun, and you have a little bit of a ring of the sun outside of that. The reason you can have these two different conditions is when the moon is closer to Earth at perigee, it's going to look a little bit bigger to us, and it will just it can completely cover the sun. When it's at apogee or away from us, it will look a little bit smaller than the disk of the sun, and you'll get this. Now, you'll only get totality or annularity if you are within these stripes over here. Anywhere else in the United States or Mexico or Canada, you are very likely to see partial eclipse, where you'll see just part of the moon cover part of the sun. And as you get close, so I know here in like where I am in Scranton, Pennsylvania, we'll get about 30% a partial eclipse, I believe, in October. So pretty much the entire United States and some of Canada and South America are going to be affected by these eclipses. Here's a movie I made of the October 14th eclipse. This is showing the percentage of eclipse that you will see from different parts at a height of 300 kilometers in the F region ionosphere. So you can see here that it really does cover pretty much the entire continental United States and gets down into South America here as well. And you can see where the moon is located. So where the moon is located, that's where annularity will occur, right there. I have a similar movie that I made for the April 8th eclipse. I'll let this play twice. So this is what the total eclipse in April is going to look like. And my collaborator, Dr. Joseph Huba from Syntec Technologies, he was formerly with Naval Research Laboratory for many years. He's the one that develops the SAMI-3 model ionosphere, and he ran a new prediction for this October's eclipse, predicting how the eclipse will actually affect the ionosphere. So this is differential total electron content from SAMI-3 for this coming October's eclipse. And you can see we really are going to have a nice hole in the ionosphere, or reduction in electron densities as a result of this eclipse. So we should be able to see the effects of the annular eclipse in our signals. One of the things that Joe pointed out that he found very interesting from running this model is if you look at the end here, I'm going to pause it. Whoops. So I can get it to pause right where I want it to stop. Yeah, right there. Okay, there you can see there's this unusual perturbation. So his model's predicting a plasma bubble that's actually a result of this eclipse. And so you can see some of the equatorial ionospheric anomaly there, where you have like hot spots here and there. And that would not be there if it were not for the eclipse. So he found that very interesting. So it'll be interesting to see if that actually shows up in the real observations. So HamSci this year is not just doing the solar eclipse QSO parties. We have a number of different experiments, and we're calling this the HamSci Festivals of Eclipse Ionospheric Science. We have multiple experiments. So we're doing the solar eclipse QSO party again, which is a traditional ham radio contest. We're going to have something called the Gladstone Signal Spotting Challenge, where we're going to award points to the best spotters using RBN, Whisper, PSK reporter spotters, people who see the most spots. We also have a GRAPE HF Doppler experiment where we're using our personal space weather stations to measure ionospheric variability as seen by observing Doppler shifts on the signals received from WWV. We have a time difference of arrival experiment, and we have more. So you can find out about all of these by going to hamsci.org/eclipse. We have some common science questions for all of these different experiments. We want to know, can you actually observe the annular eclipse in the HF communications? We predict we can, but can we actually do it? How large is the disturbance going to be? How long before and after the maximum eclipse are the eclipse effects observed? Is an onset recovery asymmetry observed? Will the results again suggest E layer propagation for 14 megahertz and F layer for 1.78 megahertz? And how similar are the eclipse effects to dawn and dusk, the gray line? And so our dates for these things, October 14th, that's coming up for the annular eclipse. We have 10 hours of operating time planned, and this is going to cover the period before the eclipse appears at all till after the eclipse is over. The solar eclipse QSO party, what we're trying to do is we're trying to take the best things that worked from the last SEQP, and we're trying to improve upon that a little bit. The bands and frequencies, we are going to take all modes, digital, all varieties, CW, and phone. The bands, we're only accepting the contest bands for the SEQP scoring, because you can't use the WARC bands for contest QSOs. For CW and sideband, you can call CQ SCQP. So we're going to encourage people to focus on the 38s. So CW plus or minus 10 kilohertz from 35, 38, 70, 38, 14, 38, etc. Sideband plus or minus 25 kilohertz from 38, 38, 72, 38, etc. And for digital modes, use the normal activity centers, but please spread out. For the QSO, for the exchange, try to give an accurate signal report. Use 4-character grid square, and you can, if you miss any information, simply ask for a repeat. The scoring is going to be the QSO points times the multipliers plus the bonus points. So again, 2 points for CW digital, 1 point for sideband, 4-character grid squares as the multipliers, and the same station may be worked for QSO points on all SEQP bands and modes. One unusual rule about this contest compared to normal contests is we're allowing dupes every 10 minutes. And this allows you to monitor changes in propagation due to the eclipse. So you can imagine that's going to be, we have a programmer, a volunteer high school student who is working on writing the scoring code for this. You can imagine that's going to be a fun rule to program into the scoring code. But we were able to do it last time, and this will give us a chance to let people make more QSOs and repeatedly test the ionosphere. So we also have the Gladstone Signal Spotting Challenge. It's a contest for people who like running skimmers or operating Whisper and FST4W. And it's named after Philip Gladstone, N1DQ. He's the founder and operator of PSK Reporter. You get 1 point for every spot received. You get a 1.25 multiplier for operating FST4W, 120 to encourage the use of that particular mode. You also get some multipliers for uploading some information about your station. So that's the contest experiments. We also have our personal space weather station Eclipse experiment. So the idea behind the personal space weather station is we want to create a receiving device that is useful for monitoring how radio wave propagation and how space weather affects radio wave propagation at your particular location. And we want to do this with a little bit more accuracy or finesse than the standard RBN or WhisperNet or FT8 receivers. And so the basic block diagram of a personal space weather station is you have a software-defined radio that's focused on the HF bands, that's connected to a GPS disciplined oscillator to provide time stamping and accurate time stamping and precision frequency measurement. You have a computer, single board computer that can process this data. You can also have a ground magnetometer. You might have a VLF receiver, and you have a this all goes out to the internet and goes to a central database. So now this is kind of the grand plan for the personal space weather station. We have, you can use any one of these instruments and still contribute to the network. So for the moment, we have teams of people who are working on helping to contribute to this. We have the ground magnetometer that's being developed by Tapper and NJIT. We have a VLF receiver that's being developed by Jonathan Rizzo. That's capturing very low frequencies, and we have some nice observations that he has captured. But what we're going to focus on for the Eclipse coming up is the device developed by Case Western Reserve University, known as the low-cost GRAPE personal space weather station. This is really a very simple radio that this is actually a very small device that will take in a signal from a Leo Bodner GPS disciplined oscillator. It'll take in a signal from an HF antenna, and it will mix the two together to give you an output, just a 1 kilohertz tone that is showing the frequency, how the frequency of the WWV carrier is shifting with time. And the reason that this is important is because WWV in Colorado has very stable, precise carrier. These GPS disciplined receivers also have very stable, precise receivers. When the ionosphere changes, it can affect the path length of the signal between the transmitter and the receiver, and that will manifest itself as very small variations in the received frequency. So you might normally think that if you're listening to WWV on 10 megahertz, you get just absolutely perfect 10 megahertz signal because that's what WWV is giving you. But in fact, if you have a sensitive enough or precise enough receiver, you'll see very small changes on the order of 0.01 or 0.1 hertz in either direction related to variations in the ionosphere. So we have some examples of this from the 2017 Eclipse. Here's WWV in Fort Collins. WA9VNJ was located near Milwaukee, and he was using a GPS disciplined receiver. And this is showing that HF Doppler shift. This is actually the day before the 2017 Eclipse, August 20th. We can use this as our control day. So here the y-axis is showing from minus 0.2 to plus 0.2 hertz. And then the x-axis is showing time from 14 to 22 UT. The dotted line here is your solar zenith angle. So when this is highest, that's when you're at noon. This is going to be noon at the midpoint between WWV and the station in Milwaukee, WA9VNJ. You can see that at dawn, you have positive Doppler shifts as the ionosphere is building up and the path lengths are becoming shorter. Things stabilize during the day. This is a solar flare creates a sudden flash, sudden bout of ionization in the ionosphere. So that creates a positive Doppler shift. And then as you go into dusk, you see these negative Doppler shifts as the ionosphere recedes. On the eclipse day, you still see the same positive Doppler shift at dawn, the negative Doppler shift at dusk. You also see, here's the eclipse effect. So here's the eclipse curve. Maximum eclipse is right here. So you get negative Doppler shift as the eclipse comes on, very similar to dusk, and you get positive Doppler shifts as the eclipse goes away, very similar to dawn. So you really can see these eclipse effects in this WWV Doppler shift. So this is a really nice example of that. So what we're doing with the new GRAPE receiver, we used to make observations that look like this, But with the new update that we're sending out and deploying right now, we're able to make spectrum measurements of around the carrier. So now just instead of getting a single measurement of the peak frequency as a function of time, you can actually see how much power spectral density is in each frequency bin as a function of time. And so this is 24 hours of observation from a day in January back in 2022. This is listening to WWV on 5 megahertz in Alabama at AB4EJ. This data is taken by Bill Engelke. And so here you can see through the night, you're getting all of these traveling ionospheric disturbances, this variation here. And then you see at dawn, you see the positive Doppler shifts, and you actually see it's much more complex than what you see even over here. You get really interesting measurements, and then things stabilize during the day. Here you can actually see separate out both the F region refraction up here, and you see the E layer refraction down there, both at the same time. So you're getting multipath signals that you're able to measure with this grape. These are measurements not taken with a grape, but by using equivalent equipment. These measurements were taken by Steve Serwin, WA5FRF, down in Texas, listening to 5 megahertz WWV. He's giving us 5 examples of what WWV Doppler shifts look like at dawn. So these are the positive Doppler shifts, and now the y-axis is time, and what it looks like at dusk. And you can see in each of these, you can see this is multipath that you're seeing here. So you can see mode splitting. This might either be 1 or 2 hops off of the F layer. It could again be E layer, 1 hop F layer, 2 hop F layer. And you can see that every single dawn is different. Every single dusk is different. And some days you have just very diffuse observations. Some days you have very discrete multipath. So this is a neat way to look at how the propagation is getting from one place to another on the HF bands. This is another way of looking at grape data. This is looking at the original grape data where you just have a single measurement as a function of time. But now what we're doing is we're looking at 10 megahertz data measured by NAOBJ. He's the person who designed the grape receiver in Cleveland, Ohio. And now I'm plotting the data colored as a function of local time between Cleveland and Fort Collins. So 24 hours of day on the y-axis, and then every day is another column on the x-axis. And so we're looking at almost 2 years worth of data here. And the colors here are Doppler shift, where the darkest blues are a half a hertz Doppler shift positive, and the brightest reds are a half a hertz Doppler shift negative. And it's really neat here because you can actually see the dawn positive Doppler shifts here, the red negative Doppler shifts at dusk over here. You can see the seasonal variation. So summer you have more daylight here, and then winter you have less daylight. So the patterns here. So you can see these seasonal variations. You can see the diurnal variations. It's really cool seeing 2 years of grape data all just lined up like this. So just neat stuff that we can see. And so what we're in the process of doing right now is we are deploying grape receivers all across the United States. This is a map I made up of where I want them to go. And just over the past week, we had a group out in New England called the New England Grape Group. They made 15 of these receivers. I actually have one sitting over here. Maybe I can show you later that we've just sent out to volunteers to help fill out this map. And then we've also had volunteers actually buy their own parts and build their own grape receivers from scratch. So I think by the time the October eclipse comes, I think we'll have somewhere between 20 to 40 of these stations, these new stations on the air. So it's really exciting. There is another technique that we can use for doing the sounding. Is measurement of the ionosphere using ham radio equipment, and this is called the time difference of arrival experiment. And This was developed by Steve Serwin, WA5FRF. He is the person that made some of those HF Doppler measurements before. You can see him here with Christina Collins, KD8OXT. She just earned her PhD from Case Western this past December on the HamSci project. So they worked together developing some of the code for this project. But the thing that's neat here is you can create a chirp waveform that you can send over a regular ham radio through the regular USB bandwidth filters, and you can see the effects of multipath by making a recording of it, and you don't need a GPS disciplined oscillator. You can just transmit with one station, make a recording with the other station, and the multipath will actually constructively interfere and deconstructively interfere at the end station, and you'll see variations in the received amplitude that you can go back and you can figure out what the characteristics of the two different signals were. And so we have, and then you can use that to back out, what layers you were hopping off of. Okay, keep going through some of this here. Let's see. Right. So if you want to participate in this, you can actually participate in this time difference of arrival event. You can go to hamsci.org. You can register at TDOA-event-2023, and you will be put into a group of hams where you'll be able to generate a custom waveform using some code online, a custom chirp waveform that'll include an ID, CW ID for your call sign, and stations will take turns sending and receiving custom chirp waveform every 6 to 10 minutes for at least 2 hours throughout the eclipse. And then you can record that to wave files, and then you can send it back to HamSci, and we will work on trying to analyze it, and you can help with the analysis too. We will show you how. This is an example of what the notebook for generating the custom waveform sounds like. And I think I can, let me reshare my screen here for a second here. I'm going to share sound. So now if I hit play, let's see if this works. Oh, you know what? I got the wrong version of the presentation here. Anyway, you can hear, if you go on the website, you can hear chirp sounds and some clicking, and you can hear Morse code over here, and you can use that to again tell, are you refracting off of just the E layer or the E and the F layer, and you can make measurements from that. So going forward, we are working on doing some test runs right now. So you can contact Steve Serwin if you want some more information about that. If you'd like to get involved with HamSci, we now have over 900 members on our listserv. You can go to hamsci.org. You can hit join HamSci, and you can join our Google group. We have telecons multiple times a week supporting the different projects. Monday night, 9 p.m. Eastern, we have the Tangerine SDR telecon. This is where we're working on developing the more advanced personal space weather station. We've taken some, in the past year or so, we've had some snags with the original Tangerine SDR plan. And so we're now working on a different plan than we originally had it based around FPGAs. We're not doing that anymore. We're using an approach that is taking advantage of Phil Karn's KA9Q's software. So we have development efforts around that on Monday nights. On Thursday mornings at 10 a.m. Eastern, we have the Grape Telecon, which is where you're doing the custom receivers to listen to WWV. And then Thursday afternoons at 4 p.m., where we have telecons to support the planning and the analysis of the solar eclipse QSO parties. This Thursday, we will not have the solar eclipse QSO party telecon. We're on break for various reasons this week, but next week, that telecon will be back. So thank you from the HamSci community. We show up to Dayton every year, and Tim has been very gracious to have me speak at Contest University and a number of his forums and that booth a couple of years ago. So thank you very much. And I want to leave you with one brand new thing that's hot off the presses. We got this from our graphics designer today. This is a draft of the Solar Eclipse QSO Party certificate of participation, which we're going to work on when you submit your logs through, I believe, Bruce Horn's website. We're going to have it automatically fill out your name and call sign here. So I'm glad that we have this up. So with that, I'll be happy to answer any questions, and thank you very much.
I have a friend out in California, Dr. Dave Leeson, who Nathaniel knows, and we call him Dr. Firehose. Nathaniel is the new Dr. Firehose. I mean, this was like drinking out of a fire hose. So thank you very much, Nathaniel. A tremendous presentation, and congratulations to you and all the people involved with HamSci. And thank you so much for presenting to the Mercer County Amateur Radio Club. And I'm glad that Josh, KJR, one of our directors, was able to join as well. Do we have any questions that we can give Nathaniel here? I think we're all just stunned. We're excited about the solar eclipse. Nathaniel, I'm sure you know that the Pennsylvania QSO Party is on top of this, and so some of our operators will be participating in the QSO parties for both the solar eclipse and the Pennsylvania QSO Party. Any questions? Yes, Ron.
Particularly in the spring, I believe the center of the eclipse will pass through Newton Falls, I believe it is.
No, you have to look at the map.
I believe so. So it would be of value to have us operating out of that area.
Well, put up a station and get after it, man.
Well, I'm asking him, could that be of value to be there
Sure.
when it comes through?
Exactly. That's exactly what he asked for.
Yeah, it's a value. Anyone who can operate in a path that goes either under, over, across the eclipse, along the eclipse path will be of value. And that's one thing that's really nice I showed before is that the eclipse is affecting all of North America. So yes, I guess stations are under the eclipse are particularly valuable, but so are stations on both sides of the eclipse. So if you want to go see the eclipse, operate from outside under while you're looking at the eclipse, go for it. If you feel like I can just stay home and this is what I can do, or I really like my contest superstation where it is and I want to operate from there, go for that. So all of these things are great. And even if you're like, it's actually really funny that the PAQP is overlaying with the Eclipse QSO Party. My local club, Murgos, they're really pushing people to do the PAQP. And I totally understand that. And I did tell them that, I put in a request to NASA to move the eclipse this year so it wouldn't conflict with the PAQP. But NASA did not deny the request, but just the way government bureaucracy works, I don't think I'm going to get the answer until after April. So, but the good news is the way the Solar Eclipse QSO Party is set up is really if you're on the air at all, especially with digital modes or CW, whether you're operating PAQP or you're operating SCQP, or if you're just operating at all, RBN, WhisperNet, PSK Reporter, they'll see you. And even if you're on phone, that's okay too. We're gonna have lots of data. The important thing is to get on the air and have a lot of fun as a ham radio operator.
One of the other great things is that Corey is recording this tonight. So in a day or two, you'll be able to replay this. And I'll be able to replay this and really try to figure some of this stuff out right from the w3lif.org website. So thank you, Corey, for recording Dave.
Yeah.
On the signals entering and the signals leaving, do they enter and leave at the same angle?
Not necessarily. The ionosphere is complex, so it's not purely specular reflection. You do get this refraction thing, and the ionosphere is not purely smooth, so the signal can go up. It might encounter an area of higher electron density, and that might cause it to refract more steeply coming out. So yeah, no, it doesn't enter and leave at the same angle. You won't get the same polarizations going in and coming out.
Now,
Complicated.
do you calculate the predictability of the shift in the angle? Or is it really not that significant?
I think certainly with the ray tracing tools that I showed you, it is absolutely possible to calculate a prediction and say, okay, how are the angles going to change? How close does that match to reality is another question. And I think that's a big area of research. Those models that we have, they're generally like smooth monthly median types of models. They're not going to have all of the actual variations that are in the ionosphere. One question is, can we take a look at the data, and can we take a look at the model, and can we use that to help understand how accurate the models are? So can we make a prediction? Yes, we can calculate it. Is that prediction reality? That remains to be seen. I think that where I showed the model and the data side by side, see if I can show that again here. At the HamSci workshop and at the University of Scranton, this past March, Joe Huba described this as a spectacular result, meaning that the observations in the model agreed well enough that we say, yeah, we're starting to head in the right direction, but there's enough disagreement where we say, okay, we have more work to do to actually understand what's going on. And I think that's where, getting those angles, predicting those angles would come into play. I think we don't have the modeling well enough to really know that for sure.
Last chance for questions, and you've got a young son to take care of. Corey, go ahead.
Just gonna say, when you talk about the model versus the reality, I think it's just truly like the amount of data, right? The amount of data in the model versus every square millimeter of the ionosphere, you can't calculate it. Right?
Exactly.
A lot of issues there.
Very, very tough. Thank you, Corey. Yes, Bruce.
Nathaniel, I got a general eclipse question for you. I've got a Cub Scout family cake event going on October the 14th, and I'm going to have a couple of hundred Cub Scout families walking around the grounds of the Cub Scout camp. You have any thoughts on any safety concerns that we might want to think about for this while this eclipse is going on?
Absolutely, there are. You definitely don't want to look at the sun directly with your own eyes. Especially without some sort of protection, especially if you're looking at partial or annular eclipse. So you can buy fairly inexpensive eclipse sunglasses. I think if you go to Eclipse, you just Google Eclipse glasses. Now there can get you go to eclipseglasses.com. I think this is a reputable site, and there are all sorts of sources of where you can get different types of eclipse glasses. When you have these glasses on, it is completely black unless you are looking at the sun. So I bought a box of 500 eclipse glasses for our students here at the university. I got that box for maybe like $300. So I would definitely make sure you have glasses like this. Also, if you go to hamsci.org, and if you go up to this meeting section, and last meeting, the one we had at Scranton, Pat Reif gave a great talk about ham radio and science, and she's also an eclipse chaser. She gave a really nice talk about some eclipse safety. You can go look at her talk on our Friday keynote video recording right here on YouTube. So that would also be good to check out.
Super. Thank you, Nathaniel. One last chance for one more question. All right, Nathaniel, thank you so much for bringing us this tonight.
Can
And
I give
thank-
a one or two more quick things?
Sure.
Very quickly. Yeah. So one thing I want to do is I want to point out that yes, we have an annual HamSci workshop, and next year we had it in Scranton this past year. Next year is going to be quite close to you. It's going to be at Case Western Reserve University, March 22nd through 23rd. So mark your calendars, and hopefully you can come join us in person in Cleveland, Ohio. Don't try to submit an abstract yet. That doesn't work. We're still working on the logistics. So this is kind of our first announcement that this is coming, but we've got that. And the other thing I want to point out is that all of this public relations, getting the word out, it's not possible without a lot of help. The HamSci team is huge. One person I'd like to a couple people I want to highlight. If you were to go to Google right now and you typed in Eclipse ionosphere, the first one of the first things that pops up says NASA solar eclipse, the impact of solar eclipse on the structure and dynamics 1 day ago. This is actually by Mackenzie Denton, KO4GLN. She is a volunteer college student from Old Dominion University, and she's their college club president down there. So she's the one that wrote that article, and she's been doing most of the HamSci Facebook page thing. So I just wanted to highlight Mackenzie. Is just doing a fantastic job, and really nice to see her participating in amateur radio like this and seeing her on the air. I also want to thank another person who's not too far away from you would be Gary McKeaton, AF8A. He is our volunteer amateur radio community coordinator. He's located in Ohio as well. So if you see him on the air, he's a big contester. And Ed Fcheck, WX2R, he is our public relations person. And they are just a few of the people who are making all of this possible. So I want to thank them.
Thank you, Nathaniel. Thank you so much for your presentation this evening. And we look forward to hearing more exciting things and the results of the solar eclipse QSO party. 73.
73, Tim and the group. Thank you so much.
And that finishes our meeting for September. 73, we're going to La Isla.
Maybe Tommy has something for you. He wants to show you. So if you have a second.
Yeah.
I've got the front.
I talked to, it's the concession.